Welcome to the Deep Dive. Today we're taking on a pretty fundamental topic, straight from the Feynman lectures. We're looking at Chapter 12, Characteristics of Force. It's all about getting past the formulas and really understanding what force is.
Exactly. And this is, crucial if you're studying physics at the college level. It's about moving beyond just plugging numbers into ESMA. Feynman jumps right in with that very equation, ESMA, and asks something profound.
Yeah, that famous one. He asks, is it just a definition, or is it actually saying something real about the universe, a law?
Right. Because if it's just a definition saying force is mass times acceleration, well, that's mathematically neat, but kind of empty, physically speaking. For FM to be a useful law, force needs to have, well, other characteristics. Independent properties.
Independent properties, like what, like how gravity works or electricity?
Precisely. Things we can measure or calculate separately from just observing acceleration. Only then does EVMA become powerful, it tells you. Calculate those courses, gravity, electrical, whatever, and then this law predicts the exact acceleration you'll get.
So it connects different aspects of physics. It's not just math, it's about observable reality, which means, and Feynman points this out, we have to deal with approximations, don't we?
Oh, absolutely. Physics is built on useful approximations. Think about defining, say, the mass of an object or even what a chair is. Math might aim for absolute precision, but physical laws, they're approximations of a messy reality. Good ones, though. They give us real insight.
Okay, let's take that idea of approximation and look at a force we encounter literally all the time. Friction. It feels real enough.
It does, but it's a classic empirical force, not fundamental. Feynman talks about two main types we sort of lump together. There's viscous drag, like air resistance on a plane, which depends on speed, maybe speed squared. And then there's the one we usually mean, sliding or dry friction.
Right, the one where we have that rule F equals mho n. Force is proportional to the normal force. Seems simple enough.
It's a great practical rule, very useful, but it's not a fundamental law of nature. You often see it explained with a block on an inclined plane, right?
Yeah, I can picture that. You've got a ramp, a block on it, the weight pulls down.
Okay, so that weight, W, you can split it. Part of it, W sine theta, tries to pull the block down the slope. The other part, W cosine theta, pushes the block into the slope. That push is the normal force, N.
And the friction force pushes back up the slope, opposing the W sine theta part.
Exactly. And the rule F mu N says that friction force is just proportional to N, that push into the surface. You can even figure out mu, the coefficient of friction, by tilting the plane until the block slides down nice and steady.
But you said it's not fundamental, so what's really going on underneath that simple mu N rule? Why isn't it like gravity?
Because if you could zoom way in, friction is, well, it's a microscopic chaos.
Yeah.
It's atoms on one surface actually sticking to atoms on the other. It's tiny bumps catching and breaking. It's energy being lost as heat, as vibrations, sound even.
So it's countless interactions averaged out.
Pretty much. Trillions and trillions of atomic interactions smoothed over into one handy number, mu. That's why it's empirical, not fundamental.
Okay, that makes sense. It's a description of a complex effect. So friction isn't fundamental. What is the force involved when things touch? You mentioned molecular forces.
Right. This is key. All contact force is friction. The force from the floor holding you up. Tension in a string. They all boil down to electrical forces between atoms and molecules.
So when I push on a wall, I'm not really touching it.
Not in the way you might think.
Ah.
Your atom's electrons are repelling the wall's atom's electrons. It's electromagnetic repulsion at incredibly short range. That's what contact is.
And Feynman visualizes this with that force versus distance graph for atoms?
Yes, figure 12-2, it shows it beautifully. When atoms are far apart, maybe a tiny attractive pull, like van der Waals forces. As they get closer, the attraction increases, up to a point. Then, try to push them too close, make their electron clouds overlap, and boom, massive repulsion.
That repulsion is what makes solids solid, right? Resisting compression.
Exactly. And there's a specific distance where the attraction and repulsion balance out perfectly. Zero net force. That's the equilibrium separation.
Okay, and what happens if you just nudge the atoms a tiny bit away from that equilibrium spot?
Well, right around that equilibrium point, if the displacements are really small, that curve looks almost like a straight line. And a force that's proportional to displacement. That's Hooke's law, the law of springs.
So Hooke's law isn't fundamental either. It's just what the electrical force looks like for small wiggles.
Oh, you got it. It's another brilliant approximation. It works incredibly well for springs and solids under small stresses, but it's just a linear snapshot of the underlying, more complex electrical interaction.
Okay, so we've peeled back friction and contact forces to reveal electrical forces. Let's talk about those fundamental forces now, starting with electricity itself. Coulomb's law.
Right, the basic interaction. Force between two charges, Q1 and Q2. It depends on how big the charges are proportional to their product, and it depends on distance. Specifically, it falls off as 1 over the distance squared, inverse square law. Like charges repel, unlike charges attract. Simple, elegant.
But then Feynman introduces a conceptual leap, moving away from just Q1 acting on Q2 directly. The field concept, you said this is crucial.
Absolutely crucial. It was a huge shift. Before fields, you had this awkward action at a distance problem. How does charge Q1 instantly know Q2 is over there to pull on it?
Feels a bit spooky.
It did. The field idea gets rid of that. Instead, we say charge Q1 doesn't act on Q2 directly. It modifies the space around itself. It creates an electric field, E, everywhere. This field, E, is a condition of space. Then, if you place another charge Q2 into that field, the field exerts the force on Q2. The force is F equals Q2 times E.
Ah, I see. So the interaction is local. The charge interacts with the field right where it is.
Exactly. And it makes calculations much more manageable, especially with lots of charges. You just figure out the total field E created by all the sources first.
Yeah.
And then you can see how that field affects any test charge you put in it.
And this whole field idea works for gravity too, right? There's a direct analogy.
A perfect analogy. If the electric field is E, we can call the gravitational field, say, C. The gravitational force on a mass m is just F equal m times c. And that gravitational field C is created by some other source mass. And guess what? It also follows an inverse square law.
It's a very similar mathematical structure. And does this field idea support superposition? Can you just add fields up?
Yes, thankfully. The principle of superposition holds. If you have multiple charges creating electric fields, the total electric field at any point is just the vector sum. You add up the arrows of the individual fields from each charge. Same for gravity.
Okay, that covers static charges and masses. But things get trickier when charges move, don't they? Electromagnetism.
They do. That's where magnetism comes into the picture as more than just static attraction or repulsion. Feynman uses the example of an electron beam in a tube, like an old TV tube.
Right, figure 12 to 3. You shoot electrons and you can steer them.
Yeah. First, you put charged plates parallel to the beam. That creates an electric field, E, perpendicular to the beam, and the electrons get deflected towards the positive plate, force FUQ, straightforward.
Okay, electric deflector.
But then you bring a magnet near the beam. Now you get a magnetic field, B. And the electrons deflect again, but the force is different. It depends not just on the charge in the field B, but also on the electron's velocity, V.
Ah, so the magnetic force only acts on moving charges.
Correct. And the force direction is weird. It's perpendicular to both the velocity and the magnetic field direction. This whole package, the electric part and the magnetic velocity-dependent part, that's the Lorentz force.
So electricity and magnetism are really tangled up, especially when things are moving.
Deeply tangled. They're really two aspects of the same fundamental interaction. Electromagnetism.
Okay, fundamental forces, empirical forces, approximations. Now, for something completely different, pseudo forces. Forces that aren't really real.
Kind of. A pseudo force isn't a real physical interaction like gravity or electricity. It's more like a bookkeeping term. You need to invent it if you're trying to apply Newton's laws, like ESMA, from inside an accelerating frame of reference, a non-inertial frame.
Accelerating frame, like being in a car when it speeds up or turns.
Exactly. Let's use Feynman's example.
Yeah.
You're inside a closed box, maybe holding a pendulum or looking at water in a jar. Suddenly, the box accelerates sideways.
What
The
happened?
pendulum swings back, the water surface tilts.
Yeah.
Someone watching from outside the box sees it clearly. The pendulum bob and the water have inertia. They resist the acceleration. The box moves out from under them, effectively.
Makes sense. Inertia.
But if you're inside the box and you don't know or you ignore that the whole box is accelerating, things look weird. The pendulum just swung backward for no apparent reason. To make FMA work in your accelerating frame, you have to invent a fake force, a pseudo force, pushing horizontally backward on everything in the box.
So you invent a force to explain the effect of the acceleration you're not accounting for.
Precisely. The most common example everyone knows is centrifugal force.
Ah, right. When you're on a merry-go-round, you feel thrown outwards.
Yes, someone watching from the ground sees you trying to go straight, inertia, while the merry-go-round floor constantly pushes you inward, centripetal force, to keep you moving in a circle. But you, on the merry-go-round, feel this strong outward push. That's the centrifugal pseudo-force. It only exists in your rotating, accelerating frame. It's not a real outward pull.
That's a trip. So these forces depend entirely on your point of view, your frame of reference.
They do. And here's where Feynman drops a mind-bending hint, connecting pseudo-forces to gravity.
Wait, how? Gravity feels pretty real.
It does. But think about it. Pseudo-forces arise because you're in an accelerating frame. Einstein's general relativity suggests that gravity, well, maybe gravity itself can be thought of as a kind of pseudo-force.
You mean like we're constantly accelerating?
In a way, the idea is that massive objects curve spacetime. What we feel is the force of gravity might just be us moving along the straightest possible path, a geodesic, through this curved geometry. It's like being in an accelerating elevator, but the acceleration is built into the fabric of spacetime itself.
Whoa. So gravity isn't a pull between masses, but just geometry in action.
That's the essence of Einstein's view, which Feynman hints at here. It reframes gravity from a force like electricity to something more fundamental related to inertia and the shape of space and time. It's deep stuff.
Seriously deep. Okay, one last category from the chapter, nuclear forces. What's the deal with them?
These are the forces holding atomic nuclei together, protons and neutrons. Their main characteristics. They're incredibly strong, but only act over extremely short distances.
How short?
Tiny. About the diameter of a proton or neutron, roughly 10 to the minus 13 centimeters. Beyond that, they basically vanish.
And strong, you mean stronger than electrical repulsion, because protons should be pushing each other apart electrically.
Much stronger. Strong enough to overcome that intense electrical repulsion between protons packed into the nucleus.
Yeah.
That's why they're called the strong nuclear force.
And unlike gravity and electricity, they don't follow that nice inverse square law.
Not at all. Their dependence on distance is much more complicated. It's often described with things like exponentials falling off incredibly sharply, like hitting a cliff rather than a gradual slope.
So calculating them must be hard.
Extremely hard. It's not a simple formula. Understanding them involves quantum field theory, the exchange of particles called mesons. It's a whole complex theoretical framework, much messier than the classical forces.
Okay, wow. We've gone from EFMA all the way to the nucleus and curved spacetime. Let's try to quickly sum up the main characteristics of force Feynman laid out.
All right. First, force isn't just a definition via EFMA. It has to be a law connecting independent properties.
Yep.
Second, many everyday forces, like friction or the stretchiness described by Hooke's law, are really just useful empirical approximations of underlying electrical forces between molecules.
Then came the huge idea of the field, replacing action at a distance with a local interaction. Charge creates a field. Field acts on charge. And that works beautifully for both electricity and gravity.
Right, and don't forget, superposition fields just add up. But then we saw complexity arises, with moving charges, bringing in magnetism via the Lorentz force.
And then the curveball, pseudo forces, forces that pop up only in accelerating frames like centrifugal force, which led to that amazing suggestion
That gravity itself might be understood as a pseudo-force arising from space-time geometry, not a traditional force between masses, a consequence of inertia in curved space.
And finally, the nuclear forces. Super strong, super short range, and mathematically complex, unlike the elegant inverse square laws.
So the big takeaway, the Feynman spirit here, is really about critical thinking. When you encounter a force in physics, you constantly need to ask, is this a fundamental law of nature?
Or is it a practical approximation that works well enough?
Or is it maybe just an artifact of my chosen perspective, my frame of reference?
It forces you to be precise about what you mean by force.
Absolutely. And maybe the final thought to leave you with is that connection between pseudo-forces and gravity. If gravity, this thing you feel constantly, isn't a pull, but is somehow equivalent to being in an accelerated system due to geometry, how does that shift your whole picture of the universe and your place in it?
Something to ponder. That's all the time we have for this deep dive into Feynman's Chapter 12. Thanks for joining us.